Hi, and welcome to the Open Fabric Alliance's 2025 webinar series. Today's topic is Libfabric, getting started with UltraEthernet. On behalf of the Open Fabric Alliance, I want to thank you for joining us today. Before I introduce our speaker, I want to touch on a couple housekeeping things that I think might be helpful for all of us. Just want to let you know that this webinar is being recorded, and both the recording of the webinar and the webinar slides will be made available on the OFA website later. We do encourage you to share the webinar with colleagues who might not have been able to join, and you'll be able to reference the slides for later reference. There will also be a brief question and answer time after the presentation if time allows. Please submit your questions in the chat tool, and we'll do our best to get to them once the presentation is over. Now I would like to introduce you to our presenter for today's webinar. Jianxin Xiong is a principal engineer at Intel. He has a rich history in various communication software stacks for HPC and AI, from MPI CCL down to kernel RDMA driver. He is currently the chair of Open Fabric's Interface Working Group and the maintainer of the Libfabric, which you can find on OFA's GitHub at the URL that's on your screen. He's an active participant in several UEC workgroups, including the software and transport working groups. Jianxin, welcome, and thank you for joining us today.
Hi, everybody. Thank you for joining. Thanks to Matt for introduction. So yeah, for today's talk, let's start with the news happening about 2 weeks ago. UltraEthernet Consortium announced the availability of the specification 1.0. It has been reported by several news media. It was a big event because it has been a few years working before the announcement. So today's talk, if we just in a sentence to summarize, we take a first look of UltraEthernet from the eyes of a Libfabric developer. So, but what is the connection between the UltraEthernet and the Libfabric? Is because Libfabric is the user space API for the UltraEthernet. So anybody want to write application utilizing UltraEthernet, we are going to use Libfabric as the API. So the outline of today's talk, we'll have 3 parts. The first part is an introduction of Libfabric. The second part is overview of UltraEthernet. And the third part is we giving some specific aspect of how to use Libfabric over UltraEthernet. We are not going to give any code example today. We are mostly focusing on the concept and some of those, items. Yeah. Okay, let's start with Libfabric. So Libfabric, also known as Open Fabric Interface or OFI, is a project under Open Fabric Alliance. It is a community-driven, low-level communication library for HPC, AI, and distributed storage. The Libfabric API, when we design the API, we consider both from the application side and the hardware side, because usually the requirement from the application side does not necessarily match what the hardware can provide. So the API is defined with to meet the application semantics. For example, the MPI and a lot of other middlewares require the tag matching. So in the Libfabric API, we have tag matching interface. And the low-level hardware, they have very different capabilities. So the Libfabric is designed so different low-level hardware is supported where we are a concept that we call the provider. So for every provider, it just work with specific hardware, and it can do hardware-specific optimization. And also the capabilities defined by the API is very rich set of API. Not every hardware can support every API or efficiently support those things. So though we have the option to provider to only support a subset of the all the API, and that those information can be discovered by the application at the runtime. Currently, we have a bunch of providers for like a verbs provider for InfiniBand and the Rocky, and TCP for socket interface, and OPX provider for OmniPath, and the UCX provider for anything running, I mean, for the IB transport with UCX on top, and the EFA for AWS uh, uh, elastic fabric, and the shared memory, and the CXI for create slingshot. And also, Libfabrics has support for GPU accelerated memory. The basic programming model for Libfabric is the queue-based asynchronous RMA operation. So basically, you have a send queue, receive queue, and completion queue. That's for posting work and checking for completions. And the API is divided into 4 parts, and there's a control part for discovering what is available on the kind of system, and the communication setup, including connection management and address vector, and also the completion for the completion queue, completion counter, and the event queues, and the data transfer functions, including message passing, tagged message passing, and RMA collectives and atomics. So Libfabric has been around for more than 10 years. We started the project in 2013, and the first stable release was on 2016. The latest release available was released this year in March at the version 2.1.0, and the upcoming release 2.2.0 is going to come out a few days from now. So we have all the links at the end of the presentation. So in Libfabric, we have many objects. So basically at top level, there's a fabric object that representing the entire network can be reached by reachable by this specific run. And the domain is the one to abstract the kind of a protection. For example, you have this memory region under the domain, and the key location is only unique. And the endpoint is the main part for the communication. So all the data transfer happens between endpoints. So in order to do this data transfer, you have to bind the endpoint with a few other objects, like a completion queue, address vector, counter. Those are necessary for facilitating the data transfer and the completion checking. And there's another queue called the event queue. That is a fabric level object. Is used for reporting asynchronous event and also connection management related event. The Libfabric supports 3 different endpoint type: FIEP message, FIEP RDM, and the FIEP datagram. The message endpoint is the connection oriented. So you have to set up the connection in advance through a similar approach, similar to what socket programming has. You do connection, and the server side have a listen and do accept. So that's server side that want to listen to accepting the connection, we call it a passive endpoint. This is showing the very left side of this graph. This is also fabric level object. And the RDM endpoint is different. It is a connectionless. Basically, you don't need to set up a connection, and you don't need a passive endpoint. So endpoint addressing the target by having the remote side address within the outgoing message. Because the remote side address usually can be complicated. I mean, it's not necessary. There's no uniform format for that. So we have this address vector to abstract that. So all the remote addresses need to be inserted into address vector. That's basically a table having the remote address internally. And the application only use the index. Is called the type FI ADDRT. So that is used for in the application. And the data ground also is transported with a connection list. You don't need to set a connection, but there's no guarantee about it's unreliable, put it simple. And the transmit size is limited, mostly to 1 MTU. Okay, the life cycle of Libfabric application start with the discovery. If I get the info, it's the one to get all the job done. After if I get the info, you got one big structure containing all the necessary information needed to initiate to create the object and initiate the communication. And there's FI version. Optionally, you can use to check the version of Libfabric library you are running today. And the second phase of initialization is including creating various objects is going to be needed, starting with the fabric, a domain, and then open the address vector, open the completion queue, counter, event queue, and the endpoint. And also including register memory region. Some of the objects may need to be enabled before finally can be used. Usually, if an endpoint needs to be enabled, memory region, depending on if the memory region is the object in the scope of domain, or if a job object in the scope of an endpoint. So it will maybe need enabled. And then the communication phase, we use various kinds of communication calls, including send receive and read write atomic operations. And also at this phase, you want to check the completion by calling the CQ read or counter read. And also EQ read will be used to check any asynchronous error or maybe connection related event. So when everything is done, the finalization phase, you don't need too much, just close all the object you have open. I mean, close all the object handles can be passed to the FI close call. Okay, now let's go to the UltraEthernet part. So what is UltraEthernet? To put it simple, it's the high performance Ethernet stack for HPC and AI. So basically, it is Ethernet, and we have a software stack that's built on top Ethernet to satisfy or to meet the demand of the modern hyperscale computing and the AI. And one of the goals is we can reach 1 million simultaneously endpoint. That's a big number. And the Ultra Ethernet is evolving the Ethernet to embrace the new level capability unavailable before on the old style like a TCP/IP or even Rocky. And this is the standard approach, not a proprietary approach. And the goal is to maximize the performance, scalability, and also maintain efficiency. Ultra Ethernet is developed by Ultra Ethernet Consortium, UEC. This is a consensus-based standard organization operating under Linux Foundation. today UEC has over 90 members, and the work under UEC define the specification is done by 8 working groups. And these 8 working groups, if you look at the picture on the right side, 4 of the groups we call the horizontal groups. They define different layer of the software, starting from the physical working group, link layer, transport layer, up to the software working group. And the other 4 groups are vertical. They define various like application usage scenario or utility or kind of functionality and management and performance debugging, compliance. Yeah, and those are crossing of all those horizontal groups because they have to interact with most of them. So as we already said, the first version of the specification was released on June 11th this year, and there's a link to get this specification, so everybody can go and download and take a look. It's totally free. So what is the benefit of UltraEthernet network? A few points here. One thing is like the UltraEthernet, the design allows out-of-order packet delivery while maintaining in-order message completion. That's make it more flexible to how the messages are delivered to the other end, and help improving the performance. And also it has the built-in security support, and also can scale and support multipassing at the packet level. And there's a multiple scheme of congestion control that make it is suitable for very busy network. And also there's other aspect like the workload tuning and the target scale of 1 million endpoints is order of magnitude higher than what is available currently for the other traditional RDMA network. So back to the specification. The specification have the content for different layers. The typical OSI network layer up to the transport. Okay, so on the top is the software layer. That is basically the defining the mapping from Libfabric API to what the UltraEthernet transport defines capable of. So it defines a lot of either some of the specific values, specific capabilities must be supported by the transport, must supported by the provider to be working correctly over the Ethernet, UltraEthernet transport. And then there's a transport layer, and this layer defines the actual what is called the UltraEthernet transport, the UET, and this define those message header formats and all those protocols in order to support delivering messages between different endpoints. And this layer has several sub layer. There's a message semantics. There's a semantics layer that defines the message transporting semantics, and the packet delivery layer depending how to deliver a single packet to the other side reliably, and the layer for the congestion management, and then the optional layer for security. And then underneath there's a network layer, but that is part is defined in the, if you look at the specification, is also in the transport. But this actually network layer specification. The optional packet trimming, this providing some mechanism to optimize the congestion control. And the link layer and the physical layer also have optional component to further helping the Ultra Ethernet protocol to run even better. So now we take a little bit of deep look into the transport layer. The transport layer is what actually make Ultra Ethernet the Ultra Ethernet. Because if you look at the below, anything below transport layer is most likely just like a ordinary Ethernet with some optional features. I mean, those features are just optional, so this can run on totally the same Ethernet what we have today. And the transport layer define all those headers and all those protocols, how those messages are delivered from one side to the other side. And inside the transport layer, as we just talked, there are semantics layer that mapping the Libfabric API to packets. So basically, it will break down a message into small packet that's going to be delivered by the lower packet deliver subsystem called PDS. And in the semantics layer, we will need to track the transactions and maintain the ordering requirement and maintain and check the completions. And the packet delivery level uh, implemented the protocol for reliable delivery if asked for, and it also need to maintain the packet ordering if that's the model you needed, and it has the ACK and NAC mechanism for all those protocols. Later we'll talk about, I mean, the ordering and the reliability is an option in the packet delivery level is determined by some types. So, and I also congestion management will limit it. I mean, just don't want the network to be overflowed by if the network cannot handle too much packet, it has to find a way to limit the rate of transmission, and also including selecting alternate paths based on the situation. And as an optional security level, do the encryption and the key management. So this transporter layer defines a set of operations, and those operations very closely map what Libfabric API does, and it is also support the authorization based on job ID. The packet delivery sublayer provide many different ordering model, including rod, RUDI, and UUD. Those are I will explain later. Just now say the quickness is like a reliable ordered delivery, reliable unordered delivery, reliable unordered delivery with idempotent operations, and unreliable unordered delivery. So we'll explain a little bit later. And the congestion control basically have two schemes. One is a network status based congestion control. The other is a receive side. I mean, control the congestion control. Basically, the first one is based on the round trip time observable from the sender side to make the decision, and the other is the receiver side based on the other informations and do the control. So, and also to simplify the implementation, a specific implementation does not necessarily to support all the features needed for the transport. So a few profiles are defined for so supporting different requirement, different application scenario. Implementation can support one or more profiles depending on the hardware capabilities. So after the transporter level, yeah, yeah, this little bit, not all the church. So overall, a packet sending out for Ultra Ethernet traffic is going to be something look like this. Is for the overall, it looks like it's an Ethernet packet. You have the Ethernet head at the beginning, and then has the IP header to route through the different switches. I mean, I using the IP routing, and there's optional UDP header. So Ultra Ethernet protocol can be implemented on top of a UDP instead of raw Ethernet. So that is optional. There are usage cases for that. At least one is you can do simplify the software emulation if you want to do some prototyping. And there's a then behind that are various Ultra Ethernet specific headers. Include you see there's a TSS headers and PDS header and SES header, and then the payload. The SES header is what we mostly focus on defining the operations opcode for at the semantic layer. So here's what is the semantic layer headers looks like. This is the standard header. It's 44 bytes. Yeah, I have put some notes there. So at the very beginning, there's a opcode defining what kind of operation it is, including write, read, atomic operations, and a fetch atomic. That is basically atomic with some data coming back, like a fetch and add, and then compare and swap. I mean those kind of things. Uh, and then yeah, also send and the tag send and some others. So, and following that, there's a bunch of flags indicating some important information about what this packet is doing. The very important thing I mentioned here is there's one completion mode. The DC is, if it is set, it requires delivery completion. That means the data has to be get into the target side, into the be handled by. I mean, not necessarily into the user buffer, but the target side has already put that data into its local buffer. Um, the REL is a relative addressing mode, so we'll talk about later. It's basically two address mode for this Ultra Ethernet transport. And the HD is called header date. It's basically if the packet is carrying an emitted data or not. So that data is going to be can be delivered to the remote side to the completion entry. And the EOM SOM just a marker for end of message or start of message. The message ID is used to distinguish uh, uh, different. I mean, if a message is sent by multiple parts, this ID can be used to associate back to what the message it is. And following that is a 64-bit address for destination. Mainly, this address is we have several sub-components there. For example, has a job ID, has a PID on fab, and a resource index. This will be explained later. But just say this all these three together is going to be we just call destination address, and then there's a buffer offset for the destination buffer, and the initiator field for specifying what the sender is. So this is used for for the receiver side can if we want to match the which sender send the message. And then following that is the memory key for the remote buffer or the match bit for tag the message. And then following is the 64-bit immediate data and the request length. And the maximum length is 4 gig minus 1 byte. So if you look at those fields, you can see those match very closely to like for example what a Libfabric send operation or write operation would have, or those parameters. I mean, can just fit here. This is the standard header. There are other kind of headers, like for example, there's an optimized header, because some operations does not have tag and does not need the key, and there's no immediate date to carry with. So for those kind of operations, you can remove those related fields. That will save a few bytes from the packet. And also there are other header format like the rendezvous extension, atomic extension, and the response. Those are used for various different protocols. So how do you know which format it is? This is determined by the PDS header. So if you remember in the previous slides, the PDS header is before the SES header. So in the PDS header, there's a field called the next header that will show what format this set header is, and also the format is also at the same time also based on this opcode. So some opcode, for example, tag the send, and that will need a tag, but it's non-tag send, so you will not need tag. So that's the basically how the transport layer, uh, delivering the information to the other side. So in the previous slide, we saw for the send, UET supports several different send operations. The most common one or most standard one is just the plain send. Is just this that we call the eager send. So the data is carried in the packet payload part, and it is delivered to the receive buffer if the matching buffer is found. However, if the matching buffer is not found at the receiver side, we have to do something I call it handling unexpected message. So handling unexpected message can be simple or can be quite complicated depending on the semantics you required. If ordered message can be more complicated. If no ordering requirement, that can be easier. But usually, you could do like a buffering, or sometimes if the buffering is consuming too much resource, you could buffer in the header and asking for retransmit in the future when the user buffer has been posted. And also, you could use some kind of explicit outside rendezvous thing to handle those things. Yeah, in the specification, there is a specific chapter talking about handling unexpected messages. And the second send is called rendezvous send. If you're familiar with MPI implementation, should know about this. Yeah, this is basically having this built into the transport layer. So this protocol will start with a request to send the packet to the other side, and this will carry the initiator buffer information, and it can optionally carry a portion of the eager date, and the other side will issue a read operation when the matching receive buffer is found, and it will send the acknowledgement when the read is done. So that is very similar to what usual rendezvous is doing. And the deferred send is a deferrable send. Is a different approach to handle this. And we can think of this as like this. This a send. You can think of it as something like a synchronous send. Basically, the send is flow controlled by the target side. So when the sender reaches the target side, if the buffer is ready, it will just process like a normal send. However, if the target is not ready, and it will hold off and sending back some acknowledgement to the sender, say, my buffer is not ready yet, so you just hold off until later notified. So later, when the buffer is ready, it will send another request to the sender, so you can restart the transmission. So that's different from the rendezvous because the restart transmission is still a send, not doing some RDMA read operation. And this usually has less overhead than rendezvous send, especially if the most of the time the buffer is already there, is expected there. For rendezvous, we always have to go to that protocol, but for deferred percent, it's optional, depending on the receive side status. So yeah, in UET, how to identify the target in the send or like in the write operation, or maybe in the receive, how to identify the source if you want to receive from a specific peer. So this is the way involving how to address the peer in UET. So the peer address consists of several parts. The first one is the fabric address. That is the network IP address for the fabric endpoint, or FEP, or FAP. So this is just the IP address. It could be IPv4 or v6. And then another part is called the PID on fab. This is a logical index within the fab. This identify a set of resources associated with a process. So this is called a PID on fab. But this PID is not the system process ID, but is we can say process ID in the view of the fab. And the job ID globally identify a job. A job can contain many processes. And also there's a resource index, or RI. This is a logical index identify a service within the process. So one process can providing, or maybe working with different services. For example, you have application using MPI and the CCL library at the same time. MPI may using one resource index, and the CCL using another resource index. So they are different services. So their resource they are not going to mix up. There are two addressing mode. The relative addressing mode, basically the PID on fab is kept in a table. So PID on fab table is per job ID. For every job has a different table. So the PID in one job can be the same as the PID on the other job. So you have to have the job ID together to uniquely identify the target address. So the target is determined by fabric address, job ID, PID on fab, and the resource index. This is used for most HPC type application, or maybe also AI application like MPI, or these are the kind of a job. And also another addressing mode called absolute addressing. You have a global PID on fab table. So all the PID on fab is unique across the entire system. So you're not going to have different, don't going to have duplication there. So the job ID is not a part of the addressing, but the job ID is used for authorization. This is useful for like a client server kind of application. So how to identify a buffer at the selected target? So you already have you send it to somebody, and the receiver side say how the message get a specific buffer. So this usually is use the tag. So if the target receive, use the tag. If the memory operation is use the memory key. However, if the receive side also requests for direct receive, and the initiate ID is also used to match the sender. And all those, in addition to this previously, also must be authorized with the job ID. Yeah, here we talk a little bit more about the profiles. As we said before, the applications have different requirements, and the implementation has different hardware capabilities. So they may optionally choose support one or more profiles. Then there are three profiles defined today: AI-based, AI-full, and HPC. And if you look at the table here, they support different subset of the operations. And the profile, look at here, the AI-full is not a subset of HPC. And when the application starts, they get the endpoint address. They will be able to negotiate the what is the common profile to support based on the endpoint address, because this is part of the endpoint address. We can see that later. Then just one note is that the AI4 is not a subset of HPC. However, with some limitation, if we use some special handling of the deferrable send, if handled as the same way as the regular send, and we can treat AI4 as a subset of HPC. So it is possible if two side, one only support AI4, the other side only support HPC. I mean, both should support AI base anyway. So it's possible they use the AI4 as the common subset instead of using AI base. Okay, yeah, let's go to the connection between Libfabric implementation and the UEC. So this is the architecture for how Ultra Ethernet fit into Libfab framework. So this Ultra Ethernet support is presented as a provider on the Libfabric. So it is in the same way as other providers does. In addition, in the kernel, there'll be vendor-specific drivers and vendor hardware, and the vendor-specific provider will talk to the driver, and also maybe through kernel bypass. There's a separate privileged entity, maybe could be job launcher, could be some key management entities. They will communicate with the driver using the UET control plan API to assign like a job ID and security keys. We note that the UET provider, we don't have a single UET provider for all the UET hardware. Basically, every vendor will supply their own providers. Then the Libfabric UET provider, they follow the same provider API as other providers does. So there's a very much possibilities the application may just work over UET by simply asking for the provider. However, the UET provider has some details that might need special attention in order to utilize all the features and avoid some discovery errors. For one example is the UET address. So not every provider have the address defined explicitly, but for UET, the address family called UFI at UET, it has been defined as this structure. In this structure, we can see we have this fabric address, that is the IP address, and the resource index, initial ID. I mean, those informations are, as we see before, are part of the way to identify the destination. And in addition, in this address also, there's a flags, and there's a capability. The flags is used to identify which of the following fields are valid, and also if the message size is limited to MTU. So that is very much to something the AI-based profile is going to be used. And also the fab cap is some bits to identify which profile this endpoint support. So by doing some bit mapping operations, the different parties can negotiate the common profile. Okay, so when doing the discovery, we want to make a note of some of the parameters. So the version have to be greater than 2.0. Otherwise, the UET provider will not return anything. And the node parameter, it must be, usually it's null, but if you set FI source in the flag, this can be non-null to identify the local node name. You cannot use node for trying to resolve the remote node. This is not supported by UET provider. And also the service is have special meaning in UET concept. The service is some name predefined, and that is can put into a configuration file loaded at the startup time, and it's basically a string followed by a range of resource indexes. So you by specifying service, you are going to set the range of the resource index for this instance of provider. And for the flag, yeah, only if now the node is non-null, you can set the FI source. Otherwise, you cannot. This flag is 0. And also in the hint, the address format must be FI address UET. Yeah, there's a question about why this is going away for allowing node. I mean, this is it's not saying going away. This is the UET provider specific limitation. The long discussion in the UET community, UEC community, and that was decided that usage model that resolving remote address through this way is not something useful in this context, and to support that basically complicated things a lot. So this is not supported in UET context. And also in the hint, the source address, you can specify a source address for as defined previously in that format, but the destination must be null. So after returning from if I get info, you could get a partial source address in the info returned that will have some basic information about this the address. Now, those are the red field in the previous slide, but the destination address is still going to be set to be null. So the endpoint assignment, assignment is done by basically the application going through the driver, and the driver talking to this, maybe talking to the privileged entity, and the entity assign all the necessary information to the driver, and the driver deliver that information back to the library. So, but anyway, in the end, the full address is retrievable through if I get a name call. So only at that time you have the full address. And also the memory region in the UET provider is always endpoint scoped. So after creating an endpoint, after creating a memory region under a domain, you have to bind the memory region with the endpoint, and then do the enabling at the end. So the application also required to set the FRMR endpoint in the hints. The memory key also have standard format. So basically, the memory key, if the totally 64 bits divided into 16 and 48, and in the higher 2 bits, there's a 1 bit called idempotent safe. That means this memory region can be used as a target for idempotent operations. idempotent operation, that means the operation can be applied more than once. So you can do the operation duplicatedly without affecting the result. An example of not idempotent safe is like a counter. If you want to use the memory region as some kind of counting something, if you do the operation twice, you will be counted twice. So that's not correct. And the O is the optimized. So that means that region can be used in the optimized headers. So that means the key only 12 the lower 12 bits of the key is significant. The 32 bits reserved space is basically not be used. Yeah, I would skip this job ID and also that authorization part because this is basically the same as what the this what Libfabric already provided today. But I just want to emphasize is this: the job ID is either user supplied or provider set. So if user set, you need to set it in various attributes. You want to set the size to be 3, and the other key to be the job ID the user got from some different place. And if the provider set, and then you set the key size to 0, and then also key to null. And then yeah, I will have leave 5 minutes for the Q&A. And so the authorization with multiple job key, this is more about this FI AV author key support. That is also part of the API already in the kind of Libfabric. But I just want to say a few words. Is that this what idea this is? You want to have one endpoint handle more than one job ID. So you want to be able to insert the authorization key into the address vector. So that address vector can be used as a that address can be used as address, but just representing a security authorization key. So you post or receive with that key as the source. So any message coming with that key is going to be acceptable. Uh, and then you can also insert another address into the address vector with a valid target endpoint, and also if I order key with that the previous created author key address as the parameter, you can get address combined with the author key. So you will be able to use that resulting address to receive message from a specific source with the specific key. So that's how it basically works. And there's another aspect is some profile limitation are mostly discoverable by if I get info. But there's one different is the maximum message size. So that one, the info you only have the maximum message size, that is maximum size for all operations. To get the detailed detailed limitation for each category, you can use the set up or get up API. I mean, mostly I think it's mainly for this AI-based profile where you have a maximum message size for the RMA, a big one, but for the message send and receive, you may only support one MTU size. And the Libfabric operations mapping to the UET transport is quite straightforward. just notice this send and the T send can map to multiple UET operations, depending on the message size and depending on this capability of this transport. Yeah, and for the delivery model, as I said, it has a reliable audio delivery. Basically, a packet delivered only once and only once. Reliable unordered delivery, delivered once and only once, but there's no ordering requirement. The RUDI is basically unordered, reliable, but the can be delivered multiple times. So that the protocol implementation have freedom to do duplication. They don't need to check for duplication. Unreliable unordered delivery, so that's the best effort. The packet could lose. So those are mapped to different endpoint types as seen in this table. And the delivery mode is part of a PDS header. So it's up if the provider implementation is responsible to choose the right method. And here are some parameters supported by the UET providers. Just the one major thing want to just to pay attention is this service path. This is the path to a config file, defining all the service available and what is the range of resource index for each of the services. The other one I want to just say one word is the maximal eager size. This is not the regular understanding of the eager size here. Here's about the eager size in the rendezvous protocol. So in the rendezvous request, you could put some part of a payload there. That is called the eager size here. As of today, we don't have any UET provider in upstream Libfabric repo. There's a reference provider in the UEC member private repo. I think work is going on to make that public at some point, and the vendors are working on their own UET providers. So getting the providers into the upstream is highly encouraged. So we want to be as many vendors and also other parties to do this as possible. And the Libfabric has many utility code that can be reduced by the UET provider implementation. And also we have some value-add utility providers. For example, the hooking providers can provide the profiling, tracing, performance statistics. And there's a links provider. You can combine multiple providers to, for example, combine with the shared memory providers. We can cover both the local node and the entire network, and also maybe to support the multi-rail in some sense, and all those will require support FI peer. So at some point, if the UET provider can have the FI peer support, that it will be naturally utilizing the function provided by the links provider. Here are some links for this information provided. Okay, let's back to the Q&A. Hopefully we can still have some. Let me look at the chat. Okay, start from the beginning. It's a list chipset that support the providers such as PSM 3. Okay, yeah, I think yeah. So the UE capabilities, the vendors is responsible for developing the provider for the hardware. For Intel chips, what I can say is, at this point we don't have this yet. So that's a quick answer. maximum is 4G. No, that is actually 4G by 1, -1, not 2G. I mean, if your message is larger than 4G, you have to, yes, application has to divide, to split up. Your sender receive based. Let rephrase that one. I mean, the provider implementation could potentially hide that from the user. I mean, it depends on what the maximum message size reported by the provider. So you have to follow that size. Will sender receive based congestion control be implemented in NIC similar? Yeah, I mean, the congestion control questions, I don't really have a good answer for that because I'm not deep into that. So maybe you want to take that question to some other people more familiar with congestion control, or looking at the specification to see if you can find more details. Yeah, the Libfabric 1.0 get info can set destination. Yeah, I think I already answered that one. Is not going away in the Libfabric API. It's just the UET provider specification are defined this way. Will there be a DNS recorder type for UEC addresses? I don't know. Yeah, maybe I can find that out later, but I don't know at this moment. Yeah, that's all the questions on the chat. Are there any other questions? Okay, I think we are over time.
Okay, thank you. Yeah, thank you, Jianxin, for your presentation, and I appreciate everyone for staying on to get these questions answered. Just as a reminder, this webinar has been recorded, and both the recording of the webinar and the webinar slides will be available on the OFA website later. So please go ahead and check it out there. Again, on behalf of the Open Fabric Alliance, thank you all for your time and for attending today's webinar.
Okay, thank you.